All right, that's recording, and that everything should be running. Good. So, reflection of light, we already talked about this very briefly before we did the lab. No need to write this all down because you already have all this information. All right, I didn't make a movie of it, but it's all there. And the thing that we discovered in the experiment, well, hopefully you've started to measure some of your angles. How is angle I related to angle R? Yep. They're equal to each other, and we call that the law of reflection. So if you have that note nearby, you can write down that right near there, the law of reflection, angle I equals angle R. You can put it right nearby, right underneath it, however you want to put that. And I'm going to then be showing you how we draw then ray diagrams in order to figure out some interesting things. Again, notice that the incident ray has an arrow pointing towards the mirror. The reflected ray has an arrow pointing away from the mirror. And so when we draw our ray diagrams, we want to make sure that we have our arrows so that it makes sense on which way the rays are going. All right? Now, what I want to talk about now is how you would draw ray diagrams. So I do want you to write this down. And I'm going to bring up the whole thing. And then we're going to draw some ray diagrams. All right, so these are the steps that you undergo when drawing ray diagrams. And today's movie is going to be a little different in that when we're done writing that down, I'm going to switch to this camera here. Now, this camera is called a video scope, and it's normally used for microscopes, but I like to almost use it as like a high-tech overhead projector. I also have my still camera here set to take video, and I'm going to then make a video of me drawing on paper instead of drawing on the smartboard. And the reason for that is the smartboard, to draw rays with rulers, well, it doesn't work. The smartboard the computer can only register one point of touch at a time. So as soon as I put a ruler on the smartboard, well, it doesn't like it. So I've got to do it with this paper so you can see what's going on. Now, rules 2, 3, and 4 do not need to be done in that order. Sometimes if I'm asking you to do a practice question, I give you the mirror and I give you the incident ray. And then you have to locate the point of incidence and draw the normal. I'll do some of the examples that way as well. So rules 2, 3, and 4 may not appear in that exact order. But once we get the normal drawn on it, we can measure the angle of incidence, and then we can determine where that ray is going to go. In physics, the purpose of physics is to look at nature and to come up with equations that explain nature, and then use those equations to predict the way nature would behave. Typically, it's in the form of like a mathematical equation. A good classic example is what we call the law of universal gravitation. which was discovered by Sir Isaac Newton. The law of universal gravitation has all kinds of interesting variables in it, m1, m2 over r squared, and that gets us the force of gravity on an object. But if we put numbers into that equation, we can predict what the force of gravity is on two objects. Now this is a little different. We do have the law of reflection, which is as discovered by yourselves and many other scientists. Angle I equals angle R. But now we want to be able to draw a diagram to predict where light will go. So that's what we're doing. We're using now the predictive power of the law of reflection. And it's really a simple law. So the pictures are fairly simple, but they do work in predicting what we see. And that's what we want to be able to do. So at this point, I'm going to keep recording the movie on the computer, but I'm going to also start to record, and if this thing shuts off every time, that's really going to get annoying. And does it zoom back out? Yeah. So let's zoom in a little bit here. All right, I like that. And I'm going to start recording this, VGA. So now the camera's also recording along with this, doesn't matter, but now I'm going to switch the input so that you can see the paper. Input. So we're recording all kinds of stuff. The camera's recording my voice, the microphone's recording my voice. But essentially I have here a nice little piece of paper, and you can put here example. So I'm going to be just working with you here, and so this is my handwriting. That's a little freaky, but that's okay. And I'm just going to, let's just put here EG, all right? And the nice thing about doing a lesson this way is that you can see the way I'm developing it. If I were to just splash a picture up on the smartboard, you wouldn't see the way I would manipulate the protractor, and you wouldn't know how to do it. So let's start by just drawing a mirror, and I'm going to have the ray coming in like this, very straightforward. So I'm going to draw the mirror, just like that. And I'm going to put some marks on the back side to represent the fact that that's the dull side of the mirror. And we'll follow the instructions just as they're stated. Let's say I don't know where the ray is coming from yet. We'll do an example like that in a moment. And let's just pick a spot on there to be the point of incidence. And now I'm going to manipulate my protractor. And many of us the other day wanted to put our protractor like this, but that's not the way we do it. We want the normal to be perpendicular to it. Now, notice this little trick. In a protractor, you'll notice that there's a little bit of plastic that kind of sticks out the end, and the 0 is up here and the 180 is down there. But this plastic, we're going to assume, is straight and is also perpendicular to this 90. So technically, we should actually, maybe we'll do it the proper way. Put a mark up here. I could have just slid the protractor back and just used the edge of the protractor, but we'll do it properly. Notice I've got the dot at that kind of vertex right there, and I'm putting my mark up there. All right? And now I'm going to take the protractor as a straight edge, and I'm going to make a straight edge right there. See how I've now moved it like a ruler? No problem. And now I'm going to put the dashed line representing the normal. And you do not need to label the normal because we draw it the same way all the time. The normal's the dashed line, the mirror is the straight line. Let's take our ruler and let's just have a ray coming in. And I really don't care what angle you choose at this point. So just have a ray coming in and hit that point of incidence. Put an incoming arrow. Doesn't matter what angle. Wilson, if you're debating on which angle you'd like. You got a favorite angle? No, just put anyone. Excellent. Taking the protractor. Again, we're always measuring from the normal. And now we're just reading an angle. Notice I'm starting on the 0. I'm not reading from the 180. So I got 10, 20, 30, 40, 50. It's looking like it's not quite to 2. So we could, oh yeah, no, it looks like 2. 1, 1, 2. So I would say for mine, it's 52.0 degrees. If it's halfway, you can put 52.5. Yours probably isn't 52. If it's not 52, don't write down 52. We got our number? Flip the protractor over to the other side. Get it on the 90. Get it on the 0. And measure out to 52. 1, 2. Put a little mark out there. Take it away. And again, you can use the straight edge of the protractor. And I'm having difficulty because I can't look down over the top because I've got various cameras in the way. Please label it as well, 52.0. Yep. No, it's okay because you've got 5 angles in there, right? So it gets pretty tight. I don't care. You can, if you did it, don't worry about it. And if you didn't, you can just put it on the table. All right? Yep. Yeah, please. Arrows in all the rays. The one's coming in, arrow in. The one's going out, arrow out. Because they're very important. Okay, let's do another one here. And let's just change things up. Because on a test, I like to change things up. This time I'm going to put the mirror this way. So there, I've got my markings like that. And this time, let's have the ray coming in before we even draw the normal. And let's have it coming from the top for no particular reason. So I'm just using the straight edge here. I'll use a ruler instead. But you could have used the straight edge. And I'm going to just have it hit right there. No particular reason. So like I said, rules 2, 3, and 4 sometimes happen in different orders. Because I could give you this picture. And there's a little assignment at the end that I ask you to do where I don't, give you the normal first. So in this case, we have to locate the normal. The point of incidence is defined as being that point where it hits. So we don't have to find it. So let's draw the normal first. You can draw it with the protractor either way. It doesn't matter. Right? You can draw it with it that way, or you can draw it with it that way. Just because of, the way I'm working down this way, I'm going to draw it this way. So again, I'm putting that 90 right on the line. I'm putting that guy on the dot. I'm marking my top end right there. I'm taking it out of the way, and I'm going to use the straight edge of the protractor to mark my normal. And again, I'm not working from the top, so you can see mine was shifted down a little bit. That was sad. I can't look straight down because of the position of the camera. You guys can get a little closer. Same thing now. Flip the protractor around, measure angle I, flip it around, measure angle R. It's not that exciting stuff, really. So here we've got angle I, always from the normal. And again, whatever your number is, because of the way I'm using the protractor, it's this outside set of numbers, 10, 20, 30, 40, it's looking like 42, 1, 2. Ooh, that's exciting. 42.0 degrees. Because you can estimate that little bit of a degree. And I'm going to flip it around. I'm going to locate the same one. I always find it interesting that when I ask students to just kind of put one in there, and I do the same thing, I always end up pretty close to 45, because you just kind of end up, you just go, oh, the middle, we'll put it in the middle. That's the way I always end up. So 42, put that on there, outcoming ray, bang, 42.0 degrees. All right? Okay? I'm not going to do any more of these with you, but like on the sheet, I have some that are on an angle where the mirror looks like this, and the ray could come in like this, right? And again, I'm just trying to mess you up. And you know what? When you're doing this as a little assignment or even on a test and I try to mess you up and you don't like it, turn the picture around so it looks like it does under normal conditions. Just turn the page over until you get it looking the way you want it to look. Put a normal on it, have the reflected ray, and you'll be just fine. Okay? All right? All right. So now the next thing I want to find, and I can switch back, I guess, to the PowerPoint. I wonder if my input button works. So the next thing I want to do, so here we've got the examples. And again, same stuff, right? Don't worry about it. Now we want to talk about how images are formed So you can put here, example, ray diagrams for images in a plane mirror. Don't write that arrow down because I'm going to switch you back to my picture, to my camera here. And I'm going to draw that for you. Just going to see if this is still recording. End up with my battery dying on me or something crazy like that. So once you get the title down, I'm going to switch back. So don't worry about that arrow. Notice the last ones we did were just rays. We were just doing reflection. Now we're going to do a ray diagram for an image. And this is what you were looking at in the second experiment. How do we find that image? So I'm going to switch back the input. We got the title? We're good? Oh, it's not liking my input button right now. Oh, success. There we go. So for this, I want you to draw a mirror, and the mirror is going to be up and down, as if you're looking into the mirror. So somewhere in the middle of your page, and this can be fairly large, make a fairly large line. There's my top, there's my bottom right there, and I'm going to put the back of the mirror over here. All right? Those of you who are very picky about your pictures, you probably don't. This one can't be close to the edge, correct, because I'm going to end up with an image on the back side. Very good. And notice how big my mirror is. It's almost as wide as the field of view there that you can see. And I better make sure I'm getting this on. My picture. Yep. So now I want to put an object out in front of that thing, and I'm going to put an arrow, and that arrow is then going to go out here. And I want it to be kind of far enough out here. And I like to put it on an angle because then it shows you how we can have different distances. And I put the arrowhead there. So notice that my arrow is about half the length of my mirror because I'm going to have some rays bouncing off of it. So here's what we call the object. I'm going to just put a big O above it. And in the lab, you guys did object 1 and object 2. I'm just going to call it O, the object. And we want to find I, the image. Okay? So what happens when you look in a mirror is you look into the mirror at home before you get to go to school, and light from the lamps that are usually above the mirror or from the side strike your face, and then all kinds of rays come off of your face. So if you imagine this as being your face, then there's all kinds of rays coming off of this object heading in all directions. But all the rays, to analyze them, are way too complicated. So we only want to analyze, well, how many rays does it take to find something in an optical thing? 2. We needed 2 to find the shadows. We need 2 to find an image. So we're going to take 2 rays that come off of this. And it doesn't matter which 2 rays. So I'm going to just have a ray that heads up, just because, and I'm going to have that ray go, and I'm going to have it hit the mirror. Now we have to do exactly what we did in the last exercise. We need to draw a normal, measure the angle of incidence, flip the protractor around, measure the angle of reflection, and draw it. All right? So we just have to get down to business at this point. I put it on there. You guys can just go ahead. I mark right there. I draw my normal. I put the protractor on there, slide it back essentially. Mine reads 25, but it looks like it's past. Slightly past 25. Ooh, that's evil. 25.1? Goodness. 25.1, 25.2 degrees. Doesn't matter. You write down whatever your number is. I'm flipping it over. I don't like this ruler. Why doesn't it have like longer lines for the 5? That's terrible. 1, 2, 3, 4, 5 and a bit. and then the ray is going to come out. Now, we've already done an activity, and we already have an idea on what we need to do in order to locate the image. What did we have to do with some of the rays in order to locate the image? Anybody remember back to Friday? Long time ago. What do we have to do? Yep. Extend the reflected rays behind. So let's go ahead and do that. I'm going to use the longer ruler here. I'm going to put it right on the line there, if I can get it right. And I'm going to extend it behind with a dashed line. Now I need a second ray. And here's where I use my brain so I don't have to work so hard. What's going to happen to a ray that comes right down straight 90 degrees from that arrowhead to the mirror? What happens to that ray, Shane? It comes straight back. Now that saves us an awful lot of work to do. Here's why. Let me show you. So if I put that right on 90, and now notice I'm using the protractor now as a flat edge. And it is. The protractors are built that way. If I put it right on 90 and right on the arrowhead, this ray is going to, I got to move it up a little bit. This ray is going to come in. It's going to hit the mirror, and then what's it going to do? Come right back. So where do I extend my ray? Straight in behind. And that is the best little cheat move. You got to arrow in, arrow out. And where our eyes perceive the meeting of the rays, we have our arrowhead. Now let's talk a little bit about the way our brains work. Our brains are excellent at following rays of light back to where they spread out from. So when a ray of light comes and hits you in the face, that light, so the light hits up from here, hits you in the face, and then the rays spread out, say from the tip of your nose. And when I look out there and I look at the tips of your nose, which is a little weird, I guess, the reason my brain can locate your nose is because it's very good at following the rays back to the point of origin. But our brains are good at doing that, but they're not very smart. So when you look in a mirror, your brains see rays coming out from the mirror. And again, our brains are good at following those rays back to the point where they appear to come from. When our brains kind of find that location on where it appears to come from, we see something. We see a thing. But in this case, we were tricked. We see an image. We don't see an object. We see where light appears to be coming from. All right? Let's do the same for the bottom side of the arrow. Doesn't matter. We could have a ray going up, but I like to put the ray down just to kind of keep it not too, kind of, I don't know, bunched up. I don't like too many rays in one spot. So we're doing the same thing. Drawing a normal. Measuring an angle eye. It's looking like I've got 22. And I know I'm going to have to extend. And now I'm going to use the most awesome ray there is, because it saves us a lot of time and effort. It's going to hit, it's going to come back, I extend in behind, and I have located the bottom of the arrow. And we could do the same thing for each point on the arrow. We could do 2 rays for here, and 2 rays for here, and 2 rays for here, and 2 rays. Really get annoying, wouldn't it? So when we find the extremes of the arrow, we say to ourselves, good enough. It's a linear thing. I connect it, and we got it. That doesn't look too bad. Now, if we did this properly, we're going to discover something useful about plane mirrors. The location of the image. If I measure from the object to the mirror, and I've got about 4.5, 6, 7, 8, I've got 4.8 centimeters, our image should be the same. And holy moly, I did it. I got a good one this year. I guarantee right now some of you are looking at your picture going, ooh, yeah, mine don't look so hot. Don't sweat about it. Any little deviation of an angle is going to bring that image in or out. Don't sweat about it, all right? When I'm marking this, say on an assignment or on a test, as long as you've done a pretty good job of measuring your angles, like if you haven't really added 5 degrees to your reflected ray, right? If you like, let's say you added 5 degrees, that's a screw up, right? But if you like kind of added like a half a degree because you were just kind of in a hurry, don't worry about it. A half a degree is enough to really shift that intersection point a lot. I'm going to check the bottom. What do we got here? I got a 3.4 centimeters. And here I got a, yeah, goodness gracious, the bottom part wasn't so good. I got a 3.7 centimeters. Ooh, not so good. Okay? All right? Questions or concerns on finding images for the plane mirrors? All right. Now, whenever we do an optical diagram, we now need to describe the image. All right? And I'm going to switch back to the PowerPoint. And if I can figure out which button to push, that would make life a little easier. So we've now drawn this. We're in good shape. That's good. And don't write this all down. This describes exactly what I described to you a moment ago. When your eyes detect light, reflected light from a plane mirror, your brain projects these light rays backwards in a straight line. This results in your brain thinking that there is a light source behind the mirror, and this is where the light rays originate from. This kind of image is called a virtual image. I'll talk more about what a virtual image is. A virtual image is an image in which light does not actually come from that location. Don't worry about that. I do want you to write down this. Characteristics of an image. We're going to be locating images quite a bit in this unit. We have to talk about images that are formed by curved mirrors, and we're going to talk about images that are formed by lenses. And every time we locate or draw or find an image, we want to describe it. And we use the acronym SALT to help us remember on what we want to describe. The S stands for size. Now, when we compare images to objects, that's what we want to compare, the image to the object. So we ask ourselves, what is the size of the image compared to the object? So it's always in comparison to the object. In a moment, I'm going to go back to the piece of paper here, and we will do the SALT for a plane mirror. But we can talk about it before we even get to writing it down. So for a plane mirror, what size is the image compared to the object? Always compared to the object. What's the size? Yep, Marissa? Same. So for a plane mirror, it's the same. We're going to find when we have curved mirrors, it's not necessarily going to be the same. If you've ever looked at yourself in the back of a spoon, that's a curved reflector. Your face doesn't look the same as it does when you look in a regular mirror. So we will obviously have different answers other than the same. Attitude. Attitude describes whether the reflection is the same way up or whether they're in opposite directions. Again, when we get talking about other types of mirrors, we're going to find that we can have an image that's completely upside down or inverted compared to the object. In this case, what is it for a plane mirror? Is it right side up, the same, upright, or is it inverted? This is not a difficult question here. What is it? Megan, what is it? It's upright. When you look at yourself in a plane mirror in the morning, you should see yourself upright just like you are, unless you're not with a spoon. And we'll get to that when we get to curved reflectors. That'll be tomorrow. Location. We want to describe the location of the image with respect to the optical device. So in this case, it's the mirror itself. So we want to describe how far away the image is from the mirror. How far is an image in a plane mirror compared to the object compared to that mirror? The same distance, we'll write it down in a moment, but the same distance behind in this case as the object is in front. We'll write that stuff down in a moment. Now, image type. There are two types of images that can exist. One is a virtual image. A virtual image is an image that the light doesn't actually come from that location. That's a tricky way to describe it. A second way to describe it is a virtual image cannot be projected onto a screen. And a third way to describe it, to see a virtual image, you have to look into the optical device. You have to look into a mirror to see your image. Real images are different. Real images, the light actually comes from that location in space. It can be projected onto a screen. Right now, you're looking at an image that is created by this projector's lens, and it actually can be projected on this screen. So this image you're looking at is a real image created by these lenses. You can't just do that with a mirror. You can't just take a mirror and project an image of somebody's face onto a wall. You have to actually be looking into the mirror to see their face. So for a plane mirror, it's a virtual image. We cannot project that. All right, let's go back to the piece of paper one more time. I want to show you one more thing, and then we're going to talk about some applications of some plane mirrors. So I'm going to switch the input back. So right now, off to the side or at the bottom, my paper can't move, so I'm going to put it off to the side. You can put it wherever you want. We're going to do the salt here. So what did we say? How's our image compared to our object? Right there? Yep. Same. Attitude. Yep. Upright. Unless you had a bad morning, and if you're looking in the mirror and you're frowning, then you've got a bad attitude. Bad attitude? No? All right. I'll keep going. Jeez, guys. These are a tough audience. Location. Where is the image located with respect to the mirror and the object? This takes usually a sentence or two, yep. Yeah, so we want to write down same distance behind mirror as object is in front. So sometimes it takes a statement to describe it. But we're describing where the image is with respect to the mirror and the object. And the type for this one is virtual. You must look into the mirror to see the image. And it cannot be projected. All right? Yep. An example of a real image? Well, this image right here is real. All right? I can project it onto something. Okay? And the light that is making that image is actual real light. So we've got actual real light striking the screen and then spreading out towards you, and you're seeing this real image right here. All right? We can make real images with curved mirrors. I'll show it. I'll explain to you later when we get to curved mirrors. So I can see the image by looking at it on the screen, but I can also see the image by looking at it down there, and it's really hard on your eyes, but you can see it down there too. Now I've got like bright spots in my eyes. But with a virtual image, I have to be actually looking in the device to see it. Okay. One last little shortcut, because I am going to get you to do, so a little shortcut. Shortcut. You can write that down. Let's draw one more mirror. Doesn't have to be big. So if I have some picture that's a little complex, like let's say the letter A. Oh, the A is an easy one. But you can kind of see there's going to be a mirror image there. Actually, A is terrible because it's symmetrical. Would have been nice to have something that wasn't symmetrical. Can I erase the A? Are you writing in pencil? I'm erasing the A. I'm making it happen. Get rid of the A. Don't like the A. I'm going to go with an F. Then, instead of drawing a bazillion rays, because I'd need 2 rays for each one of these points, what can I do to get this picture a little quicker? What could I do? I don't want to draw a million rays. I want to take a shortcut here. Yeah, Shane? Now, I don't want to draw any rays, actually. I don't want to draw any ray. What can I do to find the image? Yep. In behind the mirror. That's right. So for each important point, I'm just going to take my ruler, and there I've got like 1.2. And if I were to then double that number, 1.2, I would get then to 2.4. 2.4. There it is right there. Right? I just need to measure the same distance in behind the mirror. I actually should get a protractor out and make sure that it's perpendicular to it, but I'm not that picky on it. Yes, Shane? For something like C, you could measure various points on the curve and then just connect it with a curve. You know what I mean? So I'm going to finish this off here. I'm now going to go from the back line, and that's looking like 2.1, so I'm going to 4.2. And then down here, I'm going to go from the back line again. It's straight, so it should be 4.2. Sorry, did I say 4.2? Okay, right there. And then the front one is only 1.6. So what's that going to get me? 3.2. And then down here, 2.2, 4.4. All right. And then I can connect the dots. And again, I'm not going to be too picky about it. I'm not even going to use a ruler. Not bad. Not bad. All right? What's true about the F? What's true about images when you look into a plane mirror? Yep. They show up backwards. The image is backwards. All right? We have a term for that. I'm going to write it down in a moment here when I stop this recording and we keep going with the PowerPoint. you're going to do a little assignment on a piece of paper, and then also a question out of the textbook. And one of them involves using the shortcut. Use the shortcut for some of these complex pictures. There's even another way to do these without even measuring. I'll let you guys play around with that and see if you can figure out without even measuring. That's kind of fun. All right, so I'm going to switch back to the PowerPoint here. And I'm going to advance to the next guys here. We've done that. And I'm going to stop this, and it's already stopped, and I'm sad because I have no idea how far it went. Annoying when technology fails me. That's okay. All right. Before we talk about some applications, I want to talk about reflection off of different types of surfaces. So the first type of reflection I want to talk about is something called regular reflection, sometimes called the specular reflection, and that's essentially shiny surfaces. On shiny surfaces, light tends to reflect following the law of reflection. Light always reflects following the law of reflection, but because the surface is very smooth, the angles stay very nice. I do want you to draw a little picture for this. It's this picture here, and I'm just going to show you the way to draw that. Draw yourself a surface, put a nice mirrored surface on it, all right? And simply have a couple of rays come in and bounce out. Don't worry about measuring the ray diagrams. Just have some rays come in and bounce out and make sure they keep on going in the direction that they would go if they follow the law of reflection. It means that when the rays strike it, they stay kind of all together. Okay? So if you look at the surface of water or a mirror, right? So here, if I were to do that, I can see everybody's nice faces in there if I were to reflect that towards you. The chrome tap, even though it's a curved surface, it's still regular reflection because I can see, you know, your images in there. Their images might be distorted, but we would call that regular reflection. Okay? All right? Now, light is reflecting off of many surfaces, but it's not always regular reflection. I can see you, and I can see the desk, and I can see the wall, and I can see the paper, and I can see all of those things because light is reflecting off of it, right? The light comes from the lights. They bounce off of your face. They spread out. My eyes follow those rays back to the original point, and I locate you. But you're not shiny, so you don't reflect regularly. You're not mirrored surfaces. So what do we call that reflection that isn't shiny? We call the reflection that isn't shiny, we call it diffuse reflection. And I'm going to draw this picture with you so you can see how I want it to be drawn. But when you have an uneven surface, light rays tend to scatter because they strike the surface at many different angles. Now the picture I want you to draw is of a rough surface. Be creative. There's a rough surface there. So if we were to zoom in onto the surface of the desk, it would actually be quite rough. The wall would be rough. Your desktop would have a rough kind of surface to it. Our skin and our clothes are rough, and that's why we're not shiny like mirrors. So what happens when the light strikes it? Well, as a light ray comes in, it hits the surface, and that little piece of surface is going to have its own normal, and angle I is still going to be equal to angle R, but it may head off in that direction if the normal was right there. The normal is always in the middle. The normal is always in the middle of any single ray reflecting, because that's the way it works. But because the surface is rough, the next ray that comes along beside it might strike it like that, and if the normal is like that, then it's going to head off over there, because it struck at a different angle and had a different normal. And if one of these were to graze the top of one, it may head off over there, and its normal would have been right there. I could have dashed those normals. But notice the rays spread out. Doesn't matter how you draw it, if it looks exactly like mine or not, as long as the rays scatter. Okay? That's called diffuse reflection. Now you don't need to draw this, but an interesting thing happens when you strike a rough surface with rays that are glancing. Like, I mean really glancing. With rays that are glancing, they tend to skip over the tops, and they tend to just touch the tops, and they tend to reflect regularly. So if you take something that isn't shiny, like this textbook, it's got a kind of a bit of a shine to it. But if I turn it on an angle, I can get it to reflect nicely. The textbook doesn't work great, but my desktop works awesome. So here's my desktop right there, and you're going to want to have a good look at the desktop. If I look down at the desktop, I can kind of see my shadow in there, but I can't see my face, obviously. I couldn't comb my hair. Not that I comb my hair. But anyway, I couldn't comb my hair if I was looking at that image. But if I come way down here on an angle, I can see all of your heads floating above the desk. If you think my face looks funny, you guys look pretty funny. And if I do this type of thing here, okay, that's just weird. Could you see my reflection there? Yes, no? All right. So that's what you call, well, there's no name for it, but when the light is glancing, you get that. You might see that in the road. Let's say you're driving at night and the sun gets very close to the road. Have you ever noticed it's very bright to drive facing the sun? Because the sun is now bouncing off of the road, and the road is looking like a mirror, all right? That's often sometimes called a mirage, right? Where they say it's a mirage, a reflection of the sky in the rough surface makes it look as if it's like water. Yep. No, the sky is blue because of a scattering situation. It has to do with the particle size. It has to do with the size of the particles in the air and how the sun's light is scattered by those particles. The particles in the air are of such a size that they tend to scatter blue, and that's why the sky's blue. All right, okay. So let's talk about a few other things here. Let's not write this one down. It is in the textbook, but I don't usually have people write it down. I didn't realize this. The textbook does have a reference to it. People with dyslexia have difficulty reading print. Many people who are dyslexic complain about the glare off of the white paper. The contrast between the white paper and the black text makes it difficult reading. So some people can be helped by colored filters. That's a reflection thing. Let's talk about applications of reflection of light. So let's write down a periscope. And you're going to want to put your mirrors for this picture just kind of at 45 degrees. They don't have to be exactly 45 degrees. I'm not having you draw ray diagrams for these. They're just a little note that to kind of take a look. And when we get done the rest of the examples, I have a box of periscopes, which is fun. So we're going to just draw 2 rays here. I'm not going to draw 2 rays for each one, but we could actually draw a double ray diagram, right, where we took 2 rays and they reflected, and then they reflected again, and they continued to reflect and reflect. I'm going to just draw 1 ray representing that one that hits on, and then hits down, and then hits into your eye. And in this case, the normal is right there. So you've got here 45 degrees and 45 degrees. That's what causes the light to turn the corner. 2 45s added together. Same thing happens there. And from the bottom, the light hits. It hits down here and hits there. And in your eye, when you perceive that, you're perceiving the image in your eye. And that image actually looks like it's coming from way back here. All right? And so if you were on a submarine and that was sticking out of the water, that's how you would look out of a submarine. Actually, submarines don't use mirrors, they use prisms. So I will talk again about periscopes when we talk about light going through glass. They actually use a prism. They use a different little trick. Okay? Oh, that's an eye. See my eye? If you want to know how to draw an eye, it's really easy. Just like this. See? Do we like that eye? Like this? No? Sideways of an eye? You're not buying that? Does that make sense? You guys are very quiet today. I'm going to assume that I just have such good and entertaining information for you today that you're just taking it in. I'm going on that assumption. Rear view mirror, lateral inversion. And we already saw this when we did the example with the S. And that is a switch of left and right. And an actual application of that, well, for various, ambulance, fire trucks, etc. They will put ambulance inverted on the hood. So if you see it coming behind you in the rear view mirror, it inverts it again and makes it look normal. All right? I think they still do that. I think they still do. I'll have to check. See if maybe they don't even do that anymore. Maybe they're just expecting you to know from the lights. I'm just going to check ahead here, see if I got anything else. I'm not going to actually have you write anything down for the next 2 slides, but I do want to make reference to the question sheet for those who couldn't get it to print. Okay. I do want to show you the periscopes, and I do want to show you some plane mirrors. So I'm going to hand out some plane mirrors to everyone, and you and a partner can use the 2 plane mirrors to look at some interesting things. Before we do that, though, I'm going to stop the recording, and I'm going to talk about, well, first I'll talk about what I want you to do for your homework, then we'll play, right? We'll play with the stuff at the end, and we'll take a look at that. So, in terms of the homework, right, I have 2 things that I want you to do, and the first one is the law of reflection worksheet. And if you can't get it to print, if you could, and it's not a big deal. Oh, and the internet is just killing me here today. If you could on a screen, if you could measure that and then just draw them, you know what I mean? So, and if it's not exactly the same angle, it's not a big deal. But just draw them, all right? So with these, I ask you to measure the angles and put them on the page. Notice here I don't give you a normal, and here I'm getting you to do exactly what you did, right, in terms of our note, and then write down the salt again. And with this one, just draw it out there out front and do what you need to do, okay? So if you don't want to print it out, see if you can measure the angle on the screen. If you can, if it's approximately close, it's not a big deal. Please write in all angles. Also, I don't know if you've noticed, but I'm going to point it out here. On the day's work page, I've added one other thing on a separate piece of paper, right? Or you could even do it on the back. Part J, right, has a bunch of different things. Use the shortcut method to draw mirror images of those. So just measure. So I think they've got like 5 or 6 things. I want you to draw their mirror image as well. That'll be handed in 2 days. Okay? All right? Everybody clear on that? So textbook, part J, and you can find that textbook reference, again, on today's day's work page. Okay, and I'm going to stop the recording business here and hand out some stuff to show you.